Hey everybody, in this video lecture I'll be talking about chapter 29. For this week, instead of lectures, we're going to do chapter 29 and 30 together, at least parts of those chapters. So we're going to cover everything that you need basically for the problems at least. And this is the last material on electricity and magnetism. After this, we're going to go into thermodynamics, but we'll be doing that next week. So for chapter 29, what we're going to talk about are magnetic fields, how they're created. And the general rule is that magnetic fields are created by electric currents. Now, we're going to talk about currents in a wire, but it doesn't have to be in a wire. It could be any moving charge. So for example, the electrons moving around the nucleus in an atom will create a magnetic field. The motion or the spin of the electron around its own axis also creates a magnetic field. So anytime you have motion of a charge, basically, is when you get a magnetic field. That's how they're created. And for permanent magnets, or bar magnets, it's really those electronic motions in the atoms that create that. But for what we're going to do for the problems, we're going to look at electric currents in a wire. And as it turns out, there is a fundamental law that allows you to calculate the magnetic field if you know the currents and how they're distributed in the wires. And it's similar to Coulomb's law for the electric field, but it's more complicated. It's got a cross product in it. And I'm not going to go through the details of calculating fields from the Biot-Savart law, as it's called. I'm just going to give some results, and if you're interested in how they're calculated, they are in chapter 29. You can look at that, but I'm not going to give any problems involving that. But just be aware that there is a fundamental starting place, a fundamental law that you can calculate all magnetic fields from these, sometimes we call them filamentary currents. They're in a wire. One thing that does happen, you get a new constant, mu zero. It's kind of similar to the epsilon zero for the electric field. It's called the permeability constant, and it's defined to be 4 pi times 10 to the negative 7 Tesla meters per amp, or if you just multiply out the 4 pi, it's 1.26 times 10 to the negative 6. So that constant will appear in all of our magnetic fields, right, because it's kind of like the fundamental Coulomb constant. It's the fundamental Biot-Savart constant. So again, without doing the calculations for this, let's just show the result that you will get for a magnetic field due to a long straight wire, right? So if you got a current in a long straight wire, and it doesn't have to be a long wire if you're close to the wire, right? If you're a little tiny electron close to the wire, that wire will still look long to you. But in that case, it turns out the Biot-Savart law gives this formula for the magnetic field magnitude, the mu zero constant times the current over 2 pi r. Now r is the distance from the current perpendicular to the wire. So in this situation on the left here, I've got a current going into the page, denoted by the x. So the r is going to be the distance from that wire out to whatever point I want the field. So I can calculate the magnitude from that formula, but what about the direction? As it turns out, there is a second right-hand rule to determine the direction of the magnetic field from a current. What you do is you just put your thumb in the direction of the current, so it'll be going into the page for this left-hand side. Your fingers curl around the direction that the magnetic field goes. All right, so it'll be going clockwise in this situation with the current going into the page. On the right-hand side here, I've got an example of a current coming out. Right, well, then I'd put my thumb out of the page and my fingers would curl counterclockwise. So the direction here is counterclockwise around the current. It's always a three-dimensional thing, as usual for magnetic fields. So let's look at a situation where we've got a current going to the right, maybe. So put your thumb in the direction of the current. Your fingers curl around the wire, so they're going to be going in below the wire, going up behind it, coming out of the page above the wire, and then going down in front of the wire. So they circle around the wire. So the magnetic field will form circles around the current. And I use that right-hand rule to calculate the direction of those circles. So you can have other configurations of current, right? Not just a long straight wire. So let's look at a couple of those. You can have a current loop. So for example, let's say I've got a circular piece of wire, or it could be a number, right? It could have a number of loops of wire, kind of like our magnetic dipole that we talked about in the last chapter. Let's say I've got my current going around the circle kind of counterclockwise here. My magnetic field will point up a distance z directly above the center of the current loop. Now, to get the direction in that case, I mean, you could use your right-hand rule, right? Your thumb is in the direction of the current, so maybe you can see your fingers are going to point up. Or you could do it kind of backwards. In this case, you can put your fingers the way the current goes, and you'll see your thumb points upward in the direction of the magnetic field. But either case, if you use the Biot-Savart law, you can get the magnitude of the field or the formula for the magnitude. And notice this formula only works along the z-axis, right? It doesn't work over here. In fact, the magnetic field will kind of curve around as you go off of that z-axis. But this is the formula for the field along the z-axis, a distance z above the center of this circular current loop. One thing you can do is, let's say z is really big, so you get really far, or you could say also, maybe it's a case where this circular loop is really tiny, right? The radius of it is really small. So z becomes much bigger than the radius. Well, this formula will reduce to this magnetic dipole formula, mu0 times the magnetic moment we've talked about before, over 2 pi z cubed. And remember, the magnetic moment magnitude is the number of loops times the current times the area, right? So it would be pi r squared for the circular loop here. But again, it's the magnetic moment points in the direction of this magnetic field, upward, away from the center of the loop. Okay, so for our last example here, we're going to talk about what's called a solenoid. Now, a solenoid is a wire that's kind of wrapped into a number of turns, kind of a cylindrical thing. So I've got a space in between, right? Empty space in between these loops of wire. And I can send a current through those loops, and I will get basically a uniform or constant magnetic field inside. As it turns out, the formula for that magnetic field inside, that constant magnetic field, is mu0 times the current times the number of turns of wire divided by the length. Right, so it's kind of like a density of turns per length in the solenoid. This sort of situation is useful. This is actually how you could create an electromagnet. In fact, if you take a battery at home and some wire and wrap it around maybe a screwdriver or some piece of metal and attach it to your 9-volt battery, you'll get a pretty good magnet from that. So this is another name for this is an electromagnet. Another place this is used is in medical imaging, right? In magnetic resonance imaging, what you need is a good magnetic field. So it used to be they'd have these big cylindrical things, and they'd put the patient right in this cylinder. And so the patient would be inside here in this magnetic field, which is what you need for MRI. Apparently, people don't like to be in tight little cylinders for very long. You get claustrophobic. So now they have something called open MRI. In that case, they just have a different configuration of currents that creates a more localized magnetic field. But again, right, that's how we get magnetic fields in many cases, is due to current in a wire. And the actual strength and direction of the field just depends on how the wires are configured, kind of their geometry. But hopefully this will give you all the magnetic fields you need to use for the chapter 29 problems. We'll talk more about current in a magnetic field in the next section, and then we'll do a section or a lecture on chapter 30. but we'll stop there for this one.